This lecture will see some examples on finite gain LP stable system. So given a system, how can one establish that it is finite gain LP stable? Okay. So suppose there is a system which takes in an input and gives you a output, and how it maps is given an input. H of u is going to be a plus b tan hyperbolic of c times u. This is how it is, where a, b, c are greater than equal to 0. Okay, so we are trying to see whether the system is LP stable or not, and if LP stable for what value of p, whether it is LP stable for all values of p from 1 to infinity, or it is just L infinity stable but not LP stable when p is not infinity, and so on. Okay, here we are considering, in this example we are considering a one-dimensional system. Okay, so the output is one-dimensional and the input is also one. So it's a single input, single output system. Okay, so from the definition, so y is equal to su. So y of t is nothing but absolute value of y of t is nothing but absolute of h of u of t, which is a plus b tan hyperbolic of cut, right? This is true for all t belonging to, specifically talking of the interval 0 to infinity. Okay, and also true for all u belong, for all u mapping from 0 to infinity to r. Okay, now this is less than equal to a plus b c norm of ut. With this inequality holding, this also holds. Right. The left hand side is essentially this, and the right hand side we have this. Okay, so the system H is finite gain L infinity stable with gamma being equal to b multiplied with c and beta being equal to a. Okay, now let's say whether it is going to be LP finite gain LP stable when p is between 1 to infinity but not infinity. Okay, and for that let us see when a is 0. So for a equal to 0 is h finite gain LP stable for any p in the range 1 to infinity, excluded. Okay, so if a is equal to 0, then what we have is the y of t to be less than equal to bc norm of u of t, right? So this is from the inequality that we just started. I'm taking a to be equal to 0. So let us raise this to the power p. Both sides will raise to the power p, and the inequality will still hold because p is greater than equal to 1. So this is what we get. Okay. Now integrate both sides over the interval 0 to infinity. Dt is going to be less than equal to 0 to infinity b multiplied c to the power p norm of ut to the power p dt, and we take the pth root. If you take the pth root, then what we essentially get is that the LP norm of y is less than equal to b multiplied c multiplied by the LP norm of u. Okay, for this is holding for all p in the range 1 to infinity excluding infinity. Okay, now please note that when p is infinity, we have already established that even with a non-zero, h is finite gain L infinity stable, and the gain is bc. Okay, so if a is 0, then also it is finite gain L infinity stable. What here we are trying to show is if a is 0, is it LP stable for all other p greater than equal to 1 but less than infinity, whether it will be finite gain LP stable for them or not. Okay, so it turns out that yes, the system H is finite gain LP stable for all p in the range 1 to infinity with a equal to 0 and the gain being equal to b multiplied with c. Okay, so what you notice here is that the gain associated um, is b multiplied with c for finite gain LP stable, whether p is infinite or finite. Okay, so this system is essentially finite gain LP stable for all p's. Now, let's see if we can pick up some other signal. Okay, let's take up this. Consider a single input, single output system defined by the causal convolution So I'm taking this example from the book Nonlinear Systems by Khalil. Taking all the examples, in fact, from the book Nonlinear Systems by Khalil. Consider a seesaw system defined by the causal convolution operator yt is equal to 0 to t h t minus sigma u sigma b sigma, where ht is 0 for all t less than 0. Now suppose h is in L1 extended space. Okay, when I say h is in L1 extended space, then what does it mean? It means that any truncated version of h, which is going to be defined as this, will be essentially something of this form, because this is equal to h from 0 to tau, and then it is 0, and this guy will be finite. So this is less than infinity. So h tau's L1 now is going to be less than infinity. So that is what we mean. So suppose h is in the L1 extended space, and suppose u is in the L infinite extended space. Okay, what we want to find out is whether the system is going to be L infinite stable. So there is a system H, let us say, which takes in an input and gives you output, and the way it gives you output is through this convolution, causal convolution operation that you have. Okay, so suppose u is in L infinity, and now let's see what will happen. So suppose from the relationship that we have, this is going to hold that the absolute value of y of t is less than equal to 0 to t h t minus sigma no absolute u sigma absolute d sigma. Okay, and this is going to hold for all t in the range 0 to tau. Okay, so this is same as, I mean, this is further less than equal to supremum over all sigma in the interval 0 to tau u sigma 0 to t magnitude of h t minus sigma d sigma. Okay, now this is equal to with a change of variable I can write this as 0 to t magnitude of h of sum s ds multiplied by supremum over all sigma in the interval 0 to tau magnitude of u sigma. Okay, please note that everything here holds for all t in the interval 0 to tau. Now this I can further write as that this is less than equal to integration 0 to tau h of s ds and supremum for all sigma 0 to tau magnitude of u sigma, right? Now this thing, this inequality that you see is going to hold. So you see the right hand side is now independent of t. In this inequality, the right hand side is independent of t. So what we have here is, from this we can conclude that this norm of yt, or the magnitude of yt, is going to be less than equal to this right hand side for all t in the interval 0 to tau, which means that supremum of all t belonging to the interval 0 to tau of the magnitude yt is going to be less than equal to whatever we have here. So the right hand side is nothing but the truncated L1 norm, because this is going to be finite as given that h is in the L1 extended infinity space, and this one is going to be the truncated L infinity norm of u, is what we have, which essentially tells me that y tau L infinity norm is going to be less than h tau L1 norm and u tau L infinity norm. This inequality establishes that the system is L infinity stable. Okay, now note here, what we could establish is that the system is L infinity stable. We have not been able to establish that the system is finite gain L infinity stable. When we say finite gain L infinity stable, that scaling factor is independent of tau. But if you notice here in the inequality that you have got, the scaling factor is dependent on tau. Okay, so this is a system which is L infinity stable. The gain, or the gain factor that you see here is dependent on tau, and in actually the right hand side is going to be a class k function. Okay, in general a class k function. So that is why the system is L infinity stable. Now this was when h was in the L1 extended space. Okay, the question is, now the next question that we pose is, for the same system, what if h is in the L1 space? When h is in L1 space, it means what? That the norm of L1 norm of h, which is basically 0 to infinity mod of h sigma d sigma, is less than it. So what if h is this? So continuing from there, what we had was 0 to tau mod of h of s ds, and this guy is going to be less than equal to 0 to infinity mod of h of s ds, because if you add this 0 to infinity means you are adding more positive quantity, non-negative quantities possibly, and this is nothing but the L1 norm of H. So how does your inequality now transform when H is in L1 space rather than in L1 extended space? You have y tau L infinity. So the L infinity norm of the truncated y is going to be less than equal to L1 norm of H times L infinity norm of the truncated u. This is true for all tau in the interval 0 to infinity, and u for all u in the L infinity extended space, indicating that now with H in the L1 space, the system is finite gain L infinity stable. Okay, because the L1 norm of H is independent of tau. Is this with the gamma factor or the gain factor being norm of L1 norm of H. Okay, so uh, when H is in L1 and U is in the L infinity extended space, uh, then Y also lies in the L infinity extended space, and the system that we have in end is finitely L infinity stable with gamma equal to H of 1. Now, for the same system, we'll consider a further modified problem. What? Suppose H is L1 and U is in LP extended space for P in 1 to infinity. We've already seen what happens when P is infinity. We want to see for other P's. Suppose you have this, okay. The Y, of course, is going to be in the LP space. So the question is, so that the system is finite gain LP stable for P, for any P that you take in the range 1 to infinity. Okay, this is what has to be solved. We'll first show for P equal to 1 and then we'll show for P not equal to 1 but less than infinity. Okay, so we'll start with the convolution itself. So y of t is, we'll show this for P equal to 1 first. So y of t is given to be 0 to t h of t minus sigma u of sigma d sigma. Right. Now y tau of L1 norm of y tau is nothing but 0 to tau mod of y of t dt. Now, if we replace the expression for y of t, then what we have is 0 to t h of t minus sigma u sigma d sigma. And then you have a dt. So this is what you have. Now this is going to be less than equal to 0 to tau, then 0 to t. We can remove, we can separate out everything as h of t minus sigma mod u of sigma d sigma dt. This is same as, so we'll change the order of integration. So when we change the order of integration, this is same as saying integration 0 to tau mod of u sigma integration over sigma to tau mod of h t minus sigma dt d sigma. So this is basically what we are doing is we are changing the order of integration. So earlier we will first integrate with respect to sigma and then integrate with respect to dt. Now we are integrating first with respect to dt and then with respect to sigma. Okay, so this is what we have. Now this is less than equal to 0 to tau mod of u sigma multiplied by 0 to tau. So sigma to tau, where sigma will take values from 0 onwards, I'll say it is 0 to tau h of t minus sigma dt d sigma. This is again, in fact I'll skip some steps, and instead of saying 0 to tau, this is going to be less than equal to 0 to infinity. So I am saying the lower bound is 0 and the upper limit of integration is infinity, which means I am adding more positive value. So that is why this inequality holds, and this is nothing but this 0 to infinity mod of ht minus sigma dt is nothing but your L1 norm of h. So what you have is 0 to tau mod of u sigma into L1 norm of h d sigma, and this is nothing but equal to L1 norm of h multiplied by L1 norm of u tau. So what we have is the L1 norm of I tau being less than equal to L1 norm of h multiplied by L1 norm of u tau. Okay, so the system is finite gain L1 stable with gamma or the gain factor equal to L1 norm of h. Okay, so now we'll see for the case when p is between 1 to infinity but neither 1 nor infinity, because for 1 and infinity we have shown already how to handle things. Okay, so the t is in the range 0 to tau, and tau is something that takes values from 0 to infinity. Okay, in all cases that we have seen. So now again, using the convolution integration and the inequality, we have mod of I of t to be less than equal to 0 to t mod of h t minus sigma mod of u sigma d sigma. Right, now this is something that I can split as the following. I can write this as mod of h t minus sigma 1 by p multiplied by mod of h t minus sigma, let's say 1 by q, then mod of u sigma d sigma, where p and q are such that 1 by p plus 1 by q is 1. Okay, now this p that I have chosen is basically the p that you consider in this range 1 to infinity, and the q automatically gets determined, so that 1 by p plus 1 by q is 1. Okay, please note that from here both p and q will belong to the interval 1 to infinity. Now, before we proceed further, here I would like to highlight inequality, which is known as the Holder's inequality for L norms. Okay. Holder's inequality for L norms. What does this state? This says that if f is in LPE and g is also in LPE, where p is in the interval 1 to infinity, both endpoints excluded, and 1 by p plus 1 by q is 1. Suppose you have this, then the following holds. What is the relationship? That 0 to tau mod of f t multiplied by gt dt is going to be less than equal to 0 to tau mod of ft to the power p dt raised to 1 by p multiplied by 0 to tau mod of gt to the power q dt raised to the power 1 by q, and this holds for all tau in the interval 0 to infinity. So this is what the Holder's inequality is. If f and g are in the LP extended space with p in the range 1 to infinity, both endpoints excluded, and suppose there is a q such that 1 by p plus 1 by q is equal to 1, then this inequality holds for any value of tau in the interval 0 to infinity. Okay, so to establish that this given system, the given convolution operation is finite gain LP stable for p in the range 1 to infinity, both endpoints excluded, we'll actually need this. Okay, so we'll continue this with from the step that we had got yt to be less than equal to 0 to t mod of h t minus sigma raised to the power 1 by p mod of h t minus sigma raised to the power 1 by q mod of u sigma d sigma, where 1 by p plus 1 by q is equal to 1, and both p and q are in the interval 1 to infinity, both 1 and infinity excluded. Okay, so now I can write this as 0 to t mod of h t minus sigma to the power 1 by q and mod of h t minus sigma multiplied by u sigma to the power p raised to the power 1 by p d sigma. So this is a small rearrangement that can be done. And now from Holder's inequality, I can say that this guy here is less than 0 to t mod of h t minus sigma to the power 1 by q raised to the power q d sigma, the whole integration raised to the power 1 by q multiplied by 0 to t mod of h t minus sigma mod of um, u sigma raised to the power p, which is raised to the power 1 by p, and this is raised to the power p d sigma, and this whole integration raised to the power 1 by p. Okay, so this is nothing but equal to 0 to t mod of h t minus sigma d sigma raised to the power 1 by q, and this is 0 to t. What we have here is mod of h t minus sigma mod of u sigma raised to the power p d sigma, the whole thing raised to the power 1 by p. Okay, so now this is essentially less than equal to 0 to tau, because t is in the interval 0 to tau, so I can express it in this particular form, and I'll retain the remaining terms as they are. But in fact, better, I'll, instead of writing 0 to tau, I'll say 0 to infinity. And this is 0 to t mod of h t minus sigma mod of u sigma to the power p d sigma raised to the power 1 by p. And this is nothing but equal to the L1 norm of h raised to the power 1 by q, and then you have 0 to t mod of h t minus sigma mod of u sigma raised to the power p d sigma 1 by p. So this is what we have. The mod of y is less than equal to this relationship. Now what we'll do is we'll integrate both sides from the interval 0 to tau. Okay, so why we are doing this is basically y tau is lp norm raised to the power p is nothing but 0 to tau mod of yt to the power p dt, and this guy sitting here is nothing but less than equal to 0 to tau, and then the remaining inequality can be substituted. This is mod of p by q, I think I can take this as outside the integration because this is a constant, so I'll write it in this form. So 0 to tau, 0 to t mod of h t minus sigma mod of u sigma raised to the power p d sigma dt. This is what we have. Now again, changing the order of the integration as we did in for p equal to 1, what we get is this is going to be equal to L1 norm of h raised to the power p by q 0 to t mod of, so not say 0 to t, I should say 0 to tau. This will be 0 to tau mod of u sigma raised to the power p multiplied by sigma to tau mod of h t minus sigma. Then you have dt, and then d sigma is what you have. Now the term inside the bracket here involving mod of xt minus sigma can be um, modified as we had done earlier and expressed as, I mean, this whole quantity will be less than equal to L1 norm of h raised to the power p by q, and the bracket term is less than the um, L1 norm of h itself. Then you have 0 to tau mod of u sigma to the power p d sigma. Okay, so this is going to be L1 norm of h raised to the power p, and LP norm of u tau raised to the power p. So what we have is LP norm of y tau raised to the power p being less than equal to L1 norm of h raised to the power p multiplied by LP norm of u tau raised to the power p. So this is nothing but indicating that the finite gain LP stable inequality holds with the gain being the L1 norm of H. Okay, so this indicates that the system is finite gain LP stable for P in the range 1 to infinity with gamma equal to norm of L1. Okay, so what you see here is for p in the range 1 to infinity with 1 and infinity not excluded, the system is finite gain LP stable with the gain being the L1 norm of h. Similarly, when you had p equal to 1, let's go back to p equal to 1. When p was equal to 1, the system was finite gain L1 stable with again the gamma being the L1 norm of h, and when p was infinity, it was finite gain L infinity stable with the DC gain, or sorry, not DC gain, with the gain gamma being again the L1 norm of H. Okay, so for the seesaw system that we had been given, okay, the seesaw system that we had been given, which was basically a puzzle convolution operation of this form, for u in LPE and H in L1, the system is finite gain LP stable for P from 1 to infinity, both 1 and infinity included, with gamma equal to the L1 norm of H and beta equal to 0. Okay, so this is an example of a system which is basically um, finite gain LP stable for P in the range of 1 to infinity, both 1 and infinity 1 and infinity included, and the gain being, for all cases, the gain being L1 norm of H and beta being 0. Okay. Now, so this was for a convolution operation. We'll take one more example before we actually conclude this examples. Suppose you have a linear time invariant system of the form x dot equal to ax plus bu and y equal to cx plus du. This is a LTI system, nth order LTI system with m number of inputs and q number of outputs. And suppose A is Hurwitz. What does Hurwitz mean? It means that all the eigenvalues of A have negative real part. Okay, that is what it means. So in this case, the output yt is c e power at x0, where x0 is the initial condition, plus integration 0 to t c e power a t minus tau b u tau, or say tau, I will use sigma rather because tau is already used as some placeholder, d sigma plus du of t. Okay, so this is the system that you have in hand. So that this system is finite gain LP stable for all P in the range 1 to infinity, both 1 and infinity included. Okay, this is what has to be shown. Now, a few things to note here, right from what has been given. Let's see if we can proceed and show that this actually holds. So the few things to note here is the following. It is given that A is Hurwitz. If A is Hurwitz, then it means that the norm that you take, any norm that you take for e power at, the state transition matrix here, will always be less than equal to, I mean, there would exist a positive finite positive constant k and a finite positive constant small a, such that this is what will hold with k and a being greater than 0, and this will be true for all t greater than equal to 0. Okay, so this holds. This comes from the definition of I mean, A is Hurwitz, which means there is an exponential relationship that will occur, and this is what it comes from the definition itself. So this is what you have. Okay. Also, you see that the output y is composed of three signals. One is because of the initial condition. One is because of the interaction of the the evolution of states, so A, B, and C, and one is because of D, where the input is directly affecting the output. Okay, so what I can say is I can express y of t as y1 of t in the same the link is same as the plus. So y1 of t c e power at x0, y2 t is the integration signal, and y3 of t is nothing but du of t. Okay, so this is what we have. Now for showing that the system is finite gain LP stable, what we need to establish is that y tau LP, the LP norm of y tau has to be less than equal to some gamma LP norm of u tau plus some factor beta, where gamma and beta are non-negative finite constants, okay, independent of tau. So this is what we have to actually establish for all p in the interval 1 to infinity, both 1 and infinity included. Okay, let's start with the first. So note that uh, norm of yt is less than equal to norm of y1t. This is coming from the triangle inequality. Any norm that you wish to take for y1, y2 and y3 should suffice, but whatever norm you take, that the same norm will percolate for the definition of the LP norms. So this holds. Okay, I will start with y1. So y1 of t is c e power at x0. So the norm of y1 of t is going to be less than equal to norm of c k e power minus at norm of x0. Okay, so this is nothing but k1 e power minus at. Okay, for all t greater than equal to 0, and k1 being k norm of c norm of x0 is what k1 is. So from here what we have is y1 tau's L infinity norm is going to be less than equal to k1. Okay, this one we're talking of p equal to infinity. Also, if you see for p not equal to infinity, in that case from the inequality that we have, what we have is 0 to tau y1 t's integration dt will be always less than equal to raised to the power p, of course, is less than equal to k1 raised to the power p 0 to tau e power minus apt dt. Okay, so if you solve this, this is nothing but k1p multiplied by 1 minus e power minus ap tau divided the whole divided by ap, and this is less than equal to k1 raised to the power p divided by ap. Okay, so this indicates that the LP norm of y1 tau is less than equal to k1 multiplied by 1 by ap raised to the power 1 by p. This holds for p in the range 1 to infinity, infinity excluded. Okay, so this is for y1. What happens for y2? What is y2? y2 of t is 0 to t c e power a t minus sigma b u sigma d sigma. If you take the norm of y2, this is going to be less than equal to norm of c norm of b and then of course there is a k because there is an exponential term inside. 0 to t e power minus a t minus sigma norm of u sigma d sigma. I've skipped a few steps here. This is what we have, and this is nothing but less than equal to k2. K2 is norm of c, norm of b multiplied by k. K2 multiplied by integration 0 to t e power minus a t minus sigma norm of u sigma d sigma. Now the u that we are considering are all in the LP extended space. Please remember that. Okay. So y2 t so we have this norm of y2 of t to be less than equal to k2 0 to t e power minus a t minus sigma norm of u sigma d sigma. So from the previous example, what we see here is y2 tau's LP norm is going to be less than equal to L1 norm of h multiplied by u tau's LP norm, where h of t is nothing but e power minus at, and the L1 norm of h, which is nothing but 0 to infinity e power minus at dt, will be equal to 1 by a. Okay, so for our system here, LP norm of y2 tau is nothing but less than equal to k2 by a. So sorry, I forgot a k2 here. So k2 by a norm of LP norm of u tau. So this is what we have for all p in the range 1 to infinity, both 1 and infinity included. Okay, now come to y3. y3 of t is what? Du of t, which means that y3 of t's norm is going to be less than equal to norm of d norm of u of t, and this is nothing but some k3 norm of u of t. Okay, so this means that again y3 tau's LP norm is going to be less than equal to k3 times u tau's LP norm for all p in the range 1 to infinity. Okay, now because y t is so we have found out the components, so now we will stitch all of them together, and for that we'll use black. So we know that norm of y of t is less than equal to norm of y1 of t plus norm of y2 of t plus norm of y3 of t. So this essentially means that LP norm of y tau is less than equal to LP norm of y1 tau plus LP norm of y2 tau plus LP norm of y3 tau, and this is less than equal to some k1 times rho plus k2 by a plus k3 norm of LP norm of u tau, where this guy here is the gamma and this guy here is the beta. Now this rho is equal to 1 if p is infinity and is equal to 1 by a multiplied by p raised to the power 1 by p if p is in the range of 1 to infinity, infinity excluded. So what do we get here is that the linear time invariant system with a being Hurwitz and u taken from the LP extended space is finite gain LP stable for all p's in the range 1 to infinity, both 1 and p included. Sorry, 1 and infinity included. So I missed to write it here, so I'll write this. For all p in the range 1 and infinity, both boundaries included. Okay, so we'll stop at this example and continue our discussion in the forthcoming lectures. Thank you.